In the last video, we took a look at this plot, and we also took a look at the mode, which is the most frequently occurring value. That's one measure of what are called central tendency. So things which are in the middle of the data that we have. Another measure of central tendency is the average. So you might have seen that before. So it's also called the arithmetic mean. Let's go ahead and take a look at this. So we are going to plot the data that we saw in the very first video. This is the weight data, and as you can see, we have plotted a horizontal line over here which shows the value that I think is the central value or the average of this. So this isn't the actual average, I haven't computed it. It just seems to me that 75 is around the value where most of the things are happening, so I think that is the average. Now I've plotted this using this code, so you don't have to actually understand this code. Just go ahead and reproduce this and you will figure it out automatically. So I'll give you a brief description of this. So we are creating a figure which is 20 units wide and 5 units high. So it's kind of like a wide form. We are taking the value for weight and we are creating the x-axis based on that. So from 0 to the number of values that we have in that. The y values are going to come from the data set. Then we are going to do a scatter plot as we did earlier, and we are going to add the title and the labels. Then we are going to do this red line, this horizontal line over here, and to do that we are going to create another plot which is going to take two values, and these are going to come from this P1 and P2. Now as I said, you don't have to understand the exact semantics of the code, but what it's doing is it's taking 0 and 75 and 6000 and 75. So it's going to zip them together. So if you want to understand that, you can go ahead and print this x underscore c and y underscore c. It's not that complicated. It's just creating these values. So 0 comma 6000, so it's going to go from 0 to 6000 on the x-axis, and 75 comma 75 on the y-axis is going to remain at 75. So that creates this horizontal line. So we are simply plotting this over here in the red color and the line width of 0.75. So again, you don't have to understand the code fully because it's not that important. It's only here for the purpose of demonstrating that I think the 75 is the average. But if we actually calculate the average, it's 81, which is quite far away from 75. So in this lecture, we are trying to figure out what the actual mean is, how far is it from what seems to be the apparent mean. Okay, so let's go ahead and do this. So here we are doing two plots. One plot is simply doing the same thing as before, and the other plot is doing the mean instead of 75. So this 75 was what I thought was the central value, and this is the actual central value. So we are plotting both of them. This one, the actual value is in green, so as you can see, it's quite higher than the value that appears to me as the central value. This is going to be an important problem. The data from the real world has some sort of a problem, and in order to demonstrate that problem, we are going to take a look at a simpler collection of data. So this is our data. So these are some values, and we are going to calculate their mean. So as you can see, the mean is currently 30.625. If I go ahead and change this one value, just one final value, from 97 to 197, the mean shoots up, right? So recall what the purpose of the mean is. The mean is trying to show us what the central value is, and just by changing the value to one extreme, the center is being shifted. So think of it this way. If you're trying to calculate the average weights of people, and there just happen to be a couple of people who are overweight, extremely overweight, they are going to shift the average of the whole population. That is something that you don't want. So this guy is called an outlier. So this is essentially outside the normal, right? So that is what the outlier is. So for instance, if you have some guy at 297, it's going to shift our mean really high up. As humans, we tend to discard these outliers automatically. But when you're doing statistics, if you cannot see all the data points, and if you're looking just at the mean, you will see just this value 43.125, and you have no way of seeing that there are outliers over here, right? So let's take this back and go ahead to our paper and do some calculations to explain what the problem over here is. So this is our data. We have some values, some 16 values. So if we calculate the arithmetic mean of this, so that is going to be 30.6. Just to recall, we are going to sum over all the values that we have, and we are going to divide by the number of values, right? So sum all of these up and divide by 16, because that is the total number of values we have. The problem with this is, if you change this one value to 197, the mean shoots up to 33 or something, right? So that's a problem. What we are going to do is, we are going to take a look at another measure of central tendency, which is not going to be affected by this problem of one extreme value turning into an outlier. And here's how we're going to do this. We are going to count all the things. So these are 16 in total. We are going to split them in two, but before doing that, we have to sort them. So these are now sorted from the lower value to the highest value. So min and max at two extremes. Then we are going to take the whole set and we are going to split it into two equal parts. So these are 8 in total, and so are these, right? So by count, not by values. 8 over here, 8 over there. And this central value, we are going to call this the median, right? So what is this central value? So we have 23 over here and we have 29 on the other end. We are going to take the average of this, and that is going to turn into 26. So this 26 is our median, okay? So if we had just like an odd number of values, so for instance 1, 2, 5, 9 and 11, we would take this 5 as the median, okay? So if it's an odd number of values, you just take the central value. If it's an even number of values, you take the 2 in the middle and then you take their average, okay? So that's your median. Now let's see how this median is affected by the outlier guy that we had earlier on. So if you change this 97 to 197, your median stays at 26. It doesn't matter what you do over here. You can even change this to 1970792, whatever. It doesn't matter, because we're counting the central value, and central value is the only thing that is going to affect the median, okay? So this means that our median is robust to outliers. So robust is a very important term. What this means is, it does not get affected if you have outliers, right? So your analysis is not going to be adversely affected even if you have outliers, right? So that is the third measure of central tendency that we've seen. So we saw mode in the previous video. You have already come across the arithmetic mean. This is what people typically call the average, and we have now seen the median. So we have these three measures of central tendency, what the center of your data is, right? So we calculated the center over here. We can also go ahead and split this data into more parts. So for instance, we can split them into 4 parts. So we can take the whole data, split it into 4 equal parts. So 4 values here, 4 values here, 4 values here, and 4 values here. And we can go ahead and take this value over here and call it Q1. So this is the first quartile. This is the second quartile, which is essentially the median. We have the third quartile. So these are called quartiles. They give you a much wider description, a much more descriptive analysis of your data. You can see how the things are distributed. We'll see this in a little more detail down below. So what we can do is, we can even split them into 100 parts, right? So provided you have a sufficiently large amount of data. So for instance, if you have 1000 different data points, you can split them into 2500 equal 4 parts, okay? So you can do that, or you can split them into 100 parts of 100 values each, right? So these, if you split them into 4 parts, these are called quartiles. If you split them into 100 parts, they are called quantiles, right? So R versus N, okay? Now in order to calculate the quantile, it's not all that important how you do the calculation. I'm going to do this for the sake of completion, but we are almost always going to do this using some sort of a code. So we'll do the code as well, but let's do the calculation just briefly for the sake of completion. So what you do is, you see whichever quantile you want to calculate. So sometimes you will see this as being 25 percentile. Some people call them percentile. It's also called the 25th percentile. It's also called the first quartile. So these are all different names for the same thing. The way you do this is you take this value 0.25, you multiply it with n plus 1. So n is the number of values you have. For instance, we have 16 values over here. So n plus 1, you multiply them together, and whatever value you get, so we get 4.25. So 4.25th value is going to be our Q1, okay, or the 25th percentile or quantile. Because we are using a zero-based index, we are going to change this to 3.25th value. So the third value over here is 17 and the fourth value is 18. So let's go ahead and plot these. So this is the third value, this is the fourth value, and we want the 3.25th value. That doesn't really make sense, but the way to visualize this is you take the third value, you take the fourth value, and you go a quarter of the way ahead, right? So you go a quarter of the way from 17 to 18, and this is going to be 17.25. This is going to be 17.5. This is 17.75. So our Q1 is going to be 17.25 because we are going a quarter of the way ahead from the third value towards the fourth value. It's not all that important, and there are alternative ways of calculating this, but the thing that you have to remember is we are taking the whole data, sorting it, splitting it into 4 equal parts, and then just taking this value over here, right? So we're taking some sort of an average between these 17 and 18. Okay, so now let's go ahead and use these quantiles in a more practical way, the way you are going to see this in the real world. So here's how we're going to do this. We are going to take the minimum, we are going to put a dot on our number line. We are going to take the maximum, we are going to put a number line over here, a dot on the number line over here. We are going to take Q1, the median, or Q2, and Q3. All of these points, you just mark them, and then on the minimum put a dash over here, on the max put a dash over here, and create a box which goes from Q1 to Q3. Okay, you can create that box and split that box at the median value, and you get this weird looking thing which is called a box plot. Okay, so this is called a box plot, and this is really good for visualizing all of your data and how it's spread. From this one box plot, you can see that your median is quite low. So even though you have some outliers, so these guys are way over to the right, but your center, the center of your data is on the lower end, right? So over here, and you can see that most of your data is around here. Now this portion over here, the box portion of the box plot, that has the 50% of data. Why? Because the values below Q1 are 25% values, the values from Q3 to the max are 25%. These are 25% values by number, and these are also 25% values by number. Okay, so that turns our whole 100% values. So all the values are in this range from minimum to maximum. This range holds 25%. So for instance, if you have a box plot which looks like that, it means most of your values are very close together with very few outliers, right? Or if you have a box plot that looks like that, it means your values are very widespread, okay, and very few values are outliers. Okay, let's go ahead and take a look at all of this box plot stuff on our notebook so that you can see how to code this and how it's going to help you visualize stuff very easily. So let's go over there. So if you want to calculate the median, all you have to do is numpy.median. So there you go, 26, right? So it's as easy as that. You don't have to do the calculation by hand. Let's go ahead and take a look at the max for weight. So that's 198. The minimum is 32.4. You can calculate the median very easily. So that's 78.2. Let's go ahead and plot this. So we already plotted the mean in green. Now we are going to plot the median in red. So as you can see, our median is quite low. It's lower over here. Why is that? Because of these few outliers, right? So as you can see, there are people over here who are severely overweight, and there are only a few, but they are pushing the mean upwards. But because our median is robust to outliers, these guys do not affect our median. Okay, let's go ahead and take a look at how we can create box plots. So it's very simple. You take some data, whatever that data is. You can take a look at the median if you want. So this is the same data that we had on the notebook. We can import the statistics package, and we can do statistics.quantiles, give it the number and tell it to calculate 4 quantiles, which is essentially going to turn it into quartiles. Okay, so let's do that. As you can see, 17.25 is Q1, 26 is Q2 or the median, and 42 is the Q3. We can also do the quantiles of weight. So these are the quantiles for our weight data, and it's extremely easy to create a box plot if you use Seaborn. So you can use the box plot function of the Seaborn package and give it the weight, and it's as easy as that, right? So as you can see, this is the box plots. So this is the minimum, this is the maximum, and these are some of the things which Seaborn thinks are extreme outliers. So it simply discounts them and thinks that this is the max and these are simply outliers. So this is a facility that you get in the Seaborn package. It actually detects the outliers for you. Sometimes they're useful, sometimes they're not. It depends on what you're trying to do. We can also go ahead and create box plots based on some criteria. So the way we are doing this over here is we are saying that male weights are going to come from our DA, the original data frame, but it's going to only pick those locations, those data points or those rows in which the gender is equal to 1, and it's only going to return the column BMXWT, right? So if you do that, you get the male weights only, and if you want to take a look, these are the male weights only, right? So this is the column that we want after this criteria has been applied. So if you know SQL, you can think of this as select BMXWT from DA where RIA gender is equal to 1, right? So that's the query that we have. Okay, so let's go ahead and see what the mean for males is, and the mean for females is slightly different, slightly lower, 76. Okay, we can go ahead and plot this. We are going to do the same thing. We are going to set the style for Seaborn, and then we are going to say box plot. X is going to be RIA gender instead of the whole data frame. Y is going to be the weight, and we are going to give it data is equal to DA, right? And palette is equal to set3. It's not important what the palette is, right? So if you run that, you will see that on the x-axis we have the gender 1 and 2, and on the y-axis we have the weight, which is essentially a box plot because we asked for a box plot. So now looking at this, you can see very easily that it's easy to analyze that the median weights of females is lower than the median weights of males, and the distribution is roughly the same, right? So 50% of people are over here and 50% of females are in the lower range. So it's easy to do this analysis. You can also go ahead and change the X criteria to group people on another column, for instance the insurance thing, right? So let's go ahead and do this. So as you can see, 1.0 people, which if you recall were the people who actually did skip insurance in the past year, they have a slightly different trend in their box plot, right? So their median is slightly lower, and most of these people seem to be a little healthier in terms of their weight, right? So we're not actually doing the analysis over here, but the point is this gives you a very easy way of grouping data and taking a look at the different trends that show up just by creating a box plot. So the actual creation of the box plot in code is just this one line, right? That's it. The calculations that we did earlier, those are not going to be important if you are in computer science, because we are always going to take help from our tools and libraries, and those are going to do the grunt work for us. We do need to understand how this box plot is created, but we don't have to actually draw it by hand ever. So in this lecture, we have taken a look at the central tendency, what the center of the values is, and we have seen the concept of spread as well. How far away are things from this center, right? So from this center, these guys are a lot farther, and these guys are less further away from the median point or the center point. In the next video, we are going to quantify this concept of being away from the center point, and that is going to tell us whether almost all the people are the same in the center or if there is a lot of variation.